Good. All right. Hi, everyone. And is it? Right. Good. Today we're going to talk about eventual consistency in a distributed architecture. Oh my God. And I am a bit afraid of the number of participants we're going to have because there were like 700 participants registered to join. I'm not sure how many will make it. But this session is also recorded on YouTube. So in case you miss it or you want to share with a friend or an enemy, you can find the link in the community page. So we have a community, European software crafters, the biggest community in the world, focusing on architecture. And I should put the page of the community, right? Because the marketing part. Where are you? Come on. European software craftsmanship. Because I noticed there are more people from Europe than. So here we are doing this kind of events monthly. We hope we try. And chatting about stuff that has to do with refactoring, unit testing, and architecture. How to become better as professionals, how to work better with other humans. Oh my God. My name is victorrentea. Again, commercial spot, sorry for this moment, but I have to do it. My name is victorrentea. I've been coding for almost 2 decades, 10 years of which I've spent helping other companies or people grow and become better in this area. If you want to find more about what I do, there's a training offer over there for your company. You can Google me on YouTube. I have a lot of YouTube videos over there published. This is my legacy. When I die, people are going to look at my YouTube videos. Yeah, sure. And I have this community I just told you about. If you want to join, I'll be happy to welcome you over there. Good. And there are all sorts of raffles, all sorts of free tickets to various companies that I keep broadcasting and everything. Good. That's me. 2 children, a cat, and a garden. And I need to go on the meat. Oh, yeah. Maintaining consistency across distributed systems. I promise to have a discussion on a higher level. And I must confess that I got a lot of inspiration from the biggest e-shop in Romania, with which I had the honor to have a 2 days microservice workshop, in which, to confess, I learned more than I ever expected from those guys. And I want to share with you some of the things we learned together. I had to prepare myself, but there were really bright people over there that I got a lot to learn from. Let the saga begin. I will do my best to avoid talking about saga. You'll see, and you'll understand at the end why, I hope. So let's start with the beginning. You are distributed. Congratulations. You are partitioned on 100 machines. Bravo. The next thing you have to hear about and talk and think about is the CAP theorem. You have to talk about that a bit. CAP theorem basically says that when you are partitioned on different machines, you can either be consistent or available. You can't do both at once. What does that mean? Super simplifying the idea, imagine you have 2 databases replicating changes to each other. Whenever you insert to one of the replicas, it will push the insert over network to the other cluster, and vice versa. Now, if the network fails in between them, then the game begins. What happens if this database gets a select query? Would it return? But if it returns, it might not see the changes coming from the other server. So if you choose to respond to the select query that you get, you might be responding with stale data. I hope that's obvious. The inserts in the other replica, in the other data center, you don't see yet. Okay, that means you chose availability. The other approach would be to this query to respond with an error, which is, you know what, I can't answer that. That means why? Because I'm not sure I'm still consistent with the other guys, which means you've chosen consistency over availability. So technically, you are down when the network connection between you and your brother is corrupt, is broken. Simple as that, right? So you can't have both in a distributed ecosystem, in a distributed system. All right. Now, how do we maintain consistency in such an environment? How do we make sure that some change we want to do in different systems, imagine a flow that involves the business transaction, like buying from Glovo or from Uber Eats, something. If that spans several microservices, how do we make sure that the data that each of these microservices is stored in their database is kept in sync to understand the problem we are trying to solve today in different ways? Now, of course, before we proceed, I have to to acknowledge the fact that each service has its own database. Yeah. I mean, we are not in this scenario in which all the microservices talk to a monumental shared database. We are not in this game. We are in the game in a clean design in which each microservice has its own private database. So suddenly, the change we do in one of them has to be propagated and kept in sync with the commits happening in that database. So suddenly we have 4 transactions just to set out the environment where we are. How can we orchestrate changes happening in 2 databases so they either happen both atomically or none of them happens? Silly example, you pay the order, you ship the order. Let's super simplify this again to be clear what we're talking about. You pay the order, you ship the order. Would you imagine a scenario in which you ship the order but the payment failed? Yeehaw, right? You can't have this committing without this succeeding. So you have to keep them, the data in the 2 databases in sync. That's the game we are solving over here. Now, since the Dark Ages, since 30 years ago, this problem concerned people. And I remember myself working in systems like this in which we had like 2 large but huge databases. Typically, this database was called financing. Can you imagine this database? Financing, everything inside. And the other one was, I don't know, maybe warehousing, the whole warehousing in a single database. And sometimes we had to do changes in both at once. Yes, two-phase commit for the win. This two-phase commit is a protocol very old in which at the GDB, at the database level, at the driver level, you can orchestrate a synchronized commit. Without spending all the time with this, it's basically composed of 2 phases, of course. In the first phase, the coordinator asks all the participants, all the database, usually 2 databases, but the theory said as many. Asks all the databases, hey, are you okay with the commit? Would the commit succeed if you try to make it? I mean, would it break any foreign keys, any rules, anything? When they say okay, if everyone says okay, then the coordinator comes back and says, okay, now go, commit. Right? Green flag, everyone should push their commits in the database. Of course, things can break. If, for example, if the network fails between these 2 phases, everyone will be remaining waiting for the acknowledgement, right? Nothing comes back from the coordinator. This is not foolproof, can still fail. Requiring some recovery steps that take more than 60% of the specification of this standard. And then another problem that it involves locking. While the databases wait for the coordinator to say go, they need to wait in a state. They could block some rows. They could block some threads for update. They could have locks bound to that connection. So it doesn't scale well in a microservice. And if you play microservices and distributed systems, you probably want to scale like hell. That's why you chose microservices, to scale up or to be available. Right? So besides that, there are some resources that don't support such 2-phase commits. For example, the database should have some XA driver. This is how they are called. And furthermore, having this in place requires a GTA coordinator, at least in Java, a special orchestrator that can implement this standard, basically, right? And for extra fun, to have 2-phase commit working between microservices, it would mean that microservice 1 would have access directly to the database of microservice 2. How about that? How about APIs? You don't want to go and select and insert. Insert, can you imagine that? Service 1 inserting into service 2 databases. I mean, like, oh my God. Oh my God, right? No, just please knock on my door, send me a message or call my REST API and I'm going to insert my stuff. Don't do that. All right. Don't 2-phase commit in the database of another service. Right? So that's why it's not really fun for microservice. Now let's take a simple initial scenario to brainstorm on. And we will finish with the complex saga with a food delivery application like in this first scenario. Let's see how far we can get with this. Imagine 2 databases in the same monolith, right? User and message that's sent by a certain user, right? Now, the thing is that when you send a message as a user, you will have to be updated the last message time. So every time you do an insert of such an entity, you will have also to do an update of this entity to keep in sync the last message time of that user. This is a perfect style for a monolith. Ooh, monolith. Monolith. You can't do this insert an update in the same transaction if you are distributed into services, into databases. You can't. You just simply can't. Right? So what solution can you imagine for this? And again, this is brutal, childish, naive. Let's play the first naive idea you can get. Because when people move from in-memory method calls to microservices, wait, Bobo, are you talking still about two-phase commit? I have a question. How can we orchestrate? Well, in a two-phase commit, if in the voting phase one of them says no, then the coordinator will say rollback to all of the participants. So there is one guy who coordinates everything, who orchestrates everything, just like the Saga execution will be at the end. You will see. History would repeat itself. There is someone who keeps track of the whole flow and will say die to everyone. Right? That's the only way. Just a second to keep track of YouTube also, if there are any questions. That's apparently not yet. Good. So back on track. We have to update the last message time of the user when it sends a message. How would you do that? Well, most people, when they move to microservices forcefully, someone pushes them to microservices, they rely on API calls. So I could imagine someone, when the messaging API, when it's posted a new message, I could imagine them doing a put to the user API, that user ID, to update the message timestamp. Isn't that cute?
Isn't that cute?
But it's so wrong in so many ways. Imagine the user microservice is down. Boom. By availability, your post is gonna blow up. You see that, right? If it's doing a network call, a put, REST template, put, die, huh? It's gonna blow up. Let's not, I don't even think about optimistic locking, Peter, yet. But the point is here, this synchronous call back to another service is gonna kill you. It's fragile if the user API is down. And what if it times out? What if it times out? Would you retry? Ooh, interesting moment. We're gonna talk about that in detail in the next slide. But for now, looking at the put over here, I'm gonna say yes. After a short panic attack, I'm gonna say, oh my God, I hope I can retry it. Huh? For how long would you retry? Like what, 1 hour? what 1 hour? No, 3 times. And all sorts of pain that come along with the retries. Would you leave delay between your retries to save the server from being flooded with retries? And so much more about retries. Right? It will be soon obvious that you should not be sending a network call, a synchronous remote procedure call, a REST API call, back to the user service. So you would choose probably a message queue. An event, even better. An event sent on Rabbit on Kafka or something that will get eventually to the user. And when the user service receives the event, it will update, of course, the state of the user entity. Right? But then, you know, that guy that everything you say has a flaw? What if the Rabbit is down? Hell yes. Send the message to who? Right? If the Rabbit server is down, what would you do? We're going to solve that also later with a pattern called Transactional outbox pattern. But right now, just realize, if I'm trying to send a message, and the server, yeah, we should have a backup server. But what if my server, I don't know, with backups could work, yeah, but eesh. You should try backups first, indeed. Good. Now, in this solution, exactly, Jerica, that's where we're going. Just hold on. However, there is a third solution here, which should appear at some point. Will you start thinking of this? Just to finish with the event, there is one more funny moment. What if it sends 2 messages? But the event triggered by the first message somehow gets delayed in transit. And the second message gets first, and then, you see, one message sent first ends up received later than the previous one. Yes, you're right. I mean, from YouTube, durable queues would help, but if the server is up, if the rabbit broker is down, circuit breaker retry, people are trying shooting concept. Yes, correct. First thing first out, but how would you know? What if this message somehow, the first one that should be received first, somehow gets an error, or I don't know, maybe the listener, maybe the consumer server consumes messages on two instances, load balances the consumption, and the second instance is faster than the first one. Anything can happen. You don't have any guarantee that the message would receive in order, right? The event should be idempotent, yes. And the event to be idempotent, one of the simplest solutions on this game is to add a timestamp to the event you are sending at the sender side. In that case, when the messages get received out of order, this one is going to be ignored, saying, I don't care about that message anymore. We already have a newer timestamp than yours. That's a trick you can make to basically fix the out of order problem of the messages on the other side, right? Okay, so that's one idea. Yes, they will be retried. So if this message somehow gets rejected, it will be retried later. And in the meantime, the second one could be processed. Right. Marco, I will skip that question. It's getting more and more complex. It's getting more into message patterns. And let's stick on the consistency thing. From the consistency point of view, there is a simpler solution on the table here. Just look again at the data structures we've come from. User and message. We've just fallen into one of the most common errors in designing microservices, which is to design microservices solely based on data structures, not based on business capabilities. In other words, whose responsibility is to give you the last user timestamp message? It is this user, or is it this service's responsibility? If this guy has the history of messages from the user, why are you asking the user service to give you that? Why? Because this is the first thing we do. Because we take concepts and we put them, that you shall be named user microservice and you shall be named message microservice. Okay, that's good for high school. But then we realize that microservices should be guided by business capabilities. So the best solution for this problem is to avoid synchronization whatsoever completely between the parties and go to the message API to ask for the last message timestamp of a given user. Done. You don't need to synchronize anything anymore, right? So keep this in mind when we talk about mad kung fu things in the following. Always consider, can I redesign somehow so that I don't need to synchronize between microservice boundaries? So maintaining consistency between microservices, it's hell. Whatever you do is hell. Try to design, if these are the things that have to change in your original system, or in your overall system, and if you see that these things change together, these things change together, these things change together, and maybe these two have also changed together, don't start cutting microservices like this. You're going to kill everyone with this. Damn it, I blew it up, but you get the point. It was like this. Then try to imagine a scenario in which you cluster things by how they need to change. Maybe this could be a microservice, this could be a microservice, and this could be a microservice. And this line over here, then we pay the price. And we start thinking about the rest of the stuff that we... Object-oriented design, it's too raw level what you're saying. It's about consistency-oriented microservice breakdown, if you want, to avoid having this idea of synchronizing across microservices. However, bounded context, Peter, yes, you could play that, but bounded context smells like domain-driven, smells like solely domain concepts. These sports that were, that's too high level. Bounded context could tell you that you are in a different world, but consistency could still keep you together. Right? So consistency could still keep you as a whole, even if bounded contexts tell you to rip off from each other, right? So retry. You want to retry an action. The first thing you do, if you really want to update something on the other side of the network, the first thing to think of is retry. And when you retry, the first question to ask is idempotent. Is the operation I'm trying to repeat idempotent? We're going to use this in the end of the discussion today, you'll see. So let's first discuss idempotency. First thing, for idempotency means that an operation can be repeated without producing any additional changes on the server side, without changing further the data. So let's see. If I get the product by ID, do you think that is an idempotent operation? If I get the product by ID, is it idempotent? I'm not going to try something fun today. I'm going to fire a poll to all of you. It's where 120 in the Zoom. Do you think the get product by ID is an idempotent operation? I was explicitly looking for that result. Excellent. Good. Stop voting. Here are the results. You see, like 14 out of 63 said no, it's not idempotent. And I bet you said that because you thought of the case in which you do get twice and you get a different result back. That's not what idempotency is about. Idempotency means if you repeat a call with the database contents change, if you do two gets in the data, I agree that if you run the select twice, you might get different results. But the question is, does anything change in the database? No. Right? Ask your son to order his room. Ask your son to order his room is idempotent. Look, Antonio has a child, probably a boy. Yes, son. So Antonio asks his boy, clean your room. So he can repeat ad infinitum his request to clean the room because the effect should not change. The man just wants a clean room. If the room is clean and Antonio's son goes to clean the room, there will be no change. So it's not a problem repeating infinitely. Best example, Antonio. But this is what you tell to your colleagues, right? Cleaning a room. Clean your room. Right. What do you think about canceling a payment? Let's see in the... Yes, Amin had a suspicion there about the get. What if get inserts something in the database in YouTube? If get starts inserting stuff, it's tricky. It's tricky. Like inserting the search you made for further add, I don't know, stuff. How about canceling a payment via ID? I'm going to do the same. We will do this like 2 or 3 more times and let's relaunch. Do you think this is idempotent? Canceling a payment by ID? Would anything wrong happen if you cancel it twice? Amin looks here in YouTube, says, hey, it's a delete. If you delete twice the same resource, it shouldn't matter, right? And as a matter of fact, most payment gateways, indeed, and Paul, stop. The answer is here, yes, it is idempotent. Because if you cancel it again, you won't give more money back, right? The payment gateway, you're going to be careful about that, right? So most payment gateways allows you to cancel a payment by payment ID without any further effect. If it's already canceled, done. Right? Why is this important? To allow you to repeat the call. And as a matter of fact, as you will see later today, canceling a payment that was already made, we will name it to be a compensating transaction later today. And you can compensate a payment that was already made. And compensating actions, undoing something already done, should always be idempotent. That's a very important rule in Saga. You can reuse the ID if you don't have external keys, but the idea of the payment was given by the payment gateway before. It depends now, probably we're already talking about the concrete payment gateway, but in general, they give you an idea of the payment and that is cancelable later without any problem. Good. Update product price by ID via put. And probably they will use Jude. This is again idempotent because if you put again the same price for the same product, you want to change anything. Put should be idempotent as well as delete and get. Okay, that's like the warm-up. What do you think about place order. Do you think this is idempotent? Can you repeat this post again? That's an easy one. Have you heard about the famous problem with, I think, Food Panda in UK? Delivered the poor guy 5 orders or something like that, and asked for the money for the 5 orders? Because there was a repeat problem, there was a retry problem. And Paul, this one, you all need it, basically. As you can see, yes, this is not idempotent by default. Julia, pay attention. I did not put any order ID here. I'm just trying to create. Post is a create. But you actually nailed one good solution to this. You'll see. Come on, Gabriel. Don't mention company names, please. It's not fair. Right. Now, if you, yeah, indeed, you're also correct, William. William, nice to meet you. See you again. If you retry to create the posts, you might end up creating 2 orders. There are several solutions here. One e-shop in Romania caches the hash of your order, JSON, for some time. So if you try to order again 1 fridge, again, they won't accept the same. Wait, are you sure? 2 fridges, why, right? You want 2 bathtubs? Why? So this is one way to fix the issue on the server side, right? Like common sense, reject the order if it's the same in a time frame. Right? Common sense. Very good solution. Very good solution. Peter already has a counter use case. What if you get the special discount if you order them 1 by 1? You get the first, and you get a coupon. It's used for the second, and you get the coupon. You get for the third, and so like already Peter writes a bash script to order coffee bags with discounts from the previous order. You can't do that. However, there is one other solution that many of you already suggested in YouTube and Zoom. You could accept a unique ID from the client. Pay attention with this. You could place an order by adding like the click ID of the user in the browser, or the message ID if you have it as a message queue, and then place the order. I think there is another solution here. You could do it post, but as you mentioned in YouTube, you can do it also a put in that case. You put an order for under an ID that the client generates. This is insane. But if the client generates the ID, it can retry the put as many times they want. They won't do any damage. Otherwise, the server can deduplicate the requests, the messages, or the clicks, or the HTTP requests by checking them in a set. Again, kept for some time, probably. Place order with the ID, with the put, exactly. It's very easy because if you try to insert the same order with the same ID in the database, it's going to blow up the primary key. Right? So this is very, very good solution also for implementing idempotent message consumers. If you add to your events some unique discriminator, they could reject the duplicate. And it's very fun also for REST APIs because trying to violate the rule, it will blow up. Right? So this is idempotency. Now let's see more. More. Trying to update the database and send the message in the same time. Why am I in this game? Because if you do a REST API call, so again, folks, I want to insist just a bit more on this. This is a very good solution to implement idempotency on the server side. You allow your clients to generate the ID and you make them push a UUID. And the server can just blindly accept the ID and create the thing the client wants, and the client can repeat as many times they want. Here, message queues are more robust than doing an API call. A message queue, once you send a message on a queue, that message can be persisted if you make your queue be durable, can be stored in a database somewhere on a server, and then be pushed further to the to the recipient system when that system comes back up. It's a very good technique to not have to retry or to bang your head on how to push that change out. However, sending a message on a queue and updating your database in the same time is tricky. For example, if you send a message on a queue and the message is already out, what if the database update or commit fails afterwards? The message, you can't get it back. Not unless you involve some sort of two-phase commit between the database and the message queue broker. And there are systems, message queue systems that allow that. But again, that means a bit of risk. Not very fancy in microservices, is it? This is not wrong completely. You may want to update the database and then send the message. But what if the commit at the end fails? By the way, this is exactly the behavior you get if you write code like this in Java, at least. Because the actual send, the actual commit of this thing you inserted over here happens only when you exit the method because of this annotation. Right? So if you get to send your message out, that message is already out when the commit fails. Pay attention with this. You can be tricked. Another, probably one of the best solutions here for this constraint is to send a message after you see the commit happening. Why is this okay? Because the idea is that the chances that the message queue broker is down might be less likely than your commit to fail in the database. Hopefully. So, to do that behavior, you would use this in Spring. You would somehow run stuff after the commit of your transaction. Okay, so, but this is not entirely safe. So how can we make this safe? The pattern to use here is called transactional outbox table. You can't send and insert in the database in the same transaction easily. And you want to avoid two-phase commit. So instead of sending the message, you insert it in a table. Messages to send, right? And then you have a scheduler polling that table, seeing whether it sent all the messages on the network or not. So it's a form of persistent retry. Right? Let me show you the picture here. So your transaction is going to insert into the things you want to change, and then one more row or messages to send in the outbox table. All of this means a single commit. After that, a timer will constantly read from here and push out the messages. After it pushes the messages, you're going to remove the lines from the outbox table. This is not foolproof yet. Yeah, the message will be delivered eventually. It will be sent to Rabbit Broker eventually, right? This is not foolproof yet. Because look what happens. If this sending over here is successful, but you did not get to remove the row from the database, and there is a server crash, right? You might send the same message again when you recover. Right? Not a dead letter queue, it's a sort of a send queue or persistent, it's transactional outbox table. You need to hear about this. So you store in a table and you poll it. And there are many forms, of course, with timers, with alarms and whatever, but can end up sending duplicate messages. Folks, if you want me to read your messages, try to make them shorter. It's long messages in Zoom here, in YouTube also. I plan to take them all afterwards when you finish discussing and have a brainstorm of what you want. But if you want them to read, me to read them, make them shorter. Change the capture, of course, this is on the table here. The fancier solution on the block here, like fancy solution. Yeah, the Debidium, yeah. Which is the form of polling, but under the hood somehow, polling the database, automatically tailing the transaction log and shipping out all the inserts as messages on a Kafka. Really cool, really cool. Listen to yourself pattern means you are sending yourself a message. Here I'm technically kind of implementing a message queue. I'm persisting a message to send, and then later, 5 seconds, 1 second, very fast. I can send it. I can actually do optimizations to try to send it immediately, and if it fails, I push it there. All sorts. Good. So we finished with transactional outbox table. We finished sending the message in a robust way. We finished. We touched on the main. It feels like a whole lot more post-its. This may fail forever, and in which case you need to raise an alarm or some sort, call support or something. Now, there is one more thing to talk about, receiving a message. On the recipient side, once you get a message, you can do some updates in your database. But then there is the discussion, do you acknowledge the message to the broker as consumed successfully before? or after you insert it to your database. Most people I know are going to prefer this solution. I'm going to update my database, I'm going to commit, and then I'm going to say to Rabbit, I'm done. Or Kafka, or whatever. Now, if acknowledgement is not sent, message queue can be configured to retry the message. So you see what that means? That means that the listener that you are seeing here should be implemented idempotent. The same way, the same concept again. This is one of the most, let's say, efficient and natural way to implement message listers. Have them be idempotent, so the message you can repeat until you confirm the message. So it will fire again on this. And your update over here should somehow detect if it's a duplicate or not. Okay? Inbox pattern. Could do that also. You could store just the message in a table and then in a scheduler process it yourself. But I personally never saw that or heard that in practice. Perhaps you are more lucky. But, okay, what if I need to do over here a network call to someone else to a post? Then it's pretty simple, pretty natural. Before you do the post to another system, which is not idempotent, you need to have in a table perhaps, or in a list somehow, like the last processed messages, IDs. Writing. You keep a track of what message IDs you've seen so that you can, with an if, throw an exception if you see a duplicate. Maybe you insert those messages in an inbox seen messages table, IDs. There you go. I got the name. Wait a second. Ladies and gentlemen, we have a name. Seen messages ID table. You insert it inside, and once you see it again, you don't fire the post to the other system. Okay? Once delivery of the message is possible. Once delivery. Can you do exactly once? Yes, many systems do support that, but you need to check with your message queue provider. This behavior we are describing here can be done by all the message queue. Okay? IDs of the messages should not be identical. All right. Now, finally, let's approach the hot topic today, the saga. The saga. It's evil. Very evil. Avoid going this way. I beg you, avoid. But still, how can you run a business transaction across multiple services? You implement the business transactions, I already simplified to just mention two services with a database each. Do a business transaction spanning these two, basically composed of two separate local transactions. You let each of the services commit their changes, and you hope for the best. What about saving the data, send an acknowledgement in the database? Exactly that, Lorenzo. That's what I thought inbox pattern would mean in that case. Store the message and later process it. But store the whole message is not your game. No, just store the IDs you've seen and let the queue retry. Back here. Each local transaction of a microservice would send the message, because this is a robust way, to the next party in the game, the next in the chain. An event or a command, another discussion, very interesting, but I'm not sure you can have the time to go there. Command would be targeting a single system. Event would be a broadcast to whoever is interested to listen. Right? And based on these messages, another next service would commit another local transaction for itself. Good. Now, if any of these local transactions fails along the way, the saga is basically a pattern for automatically error recovery. The saga can execute compensating transactions to undo the previously committed transaction. So technically speaking, it will go to if service 1 says, okay, I'm done, but then service 2 down the chain says, oops, sorry, in red, then service 1 has to undo what he did, right? Cancel the payment, cancel the stock reservation, whatever. That means that the saga pattern is in charge to tell that guy to cancel. That's called the compensating transaction. One more endpoint, one more pleasure, one more queue, whatever. Right? So compensating action. Another thing here, I told you at the beginning, in the first system, that's a very fun moment. I'm not sure you can understand it that fast, but imagine that if you want to compensate a failure of the second system, going to the first system, tell it to cancel. Imagine what will happen if the cancellation fails. And you're trying to give someone money back on the card, but that guy used a one-shot virtual card that was already closed by then. What do you do? In theory, in practice, in Saga, the compensating transactions need to be repeatable, needs to be idempotent. So you should not ever fear of retrying as many times until you get the confirmation from that. It's very important. And get the free fridge. Right. Now, there are some things in real life. I get some things in real life that can't really be undone, for which we would use reservations. Yes, indeed, Wolfgang, you are right in there. I'm going to say that at some point, that it is cheaper at the end of everything. I'm going to warn you that you should avoid Saga. One of the first things that you also mentioned here, if you want to cancel a previously completed transaction, one of the first options you have on the table is to call support. Support. And support are going to do a data fix in the database, fixing your problem. And you do that a lot of times until it becomes too expensive. Until it becomes too expensive to continue doing that. My video is dead. That's interesting. I don't know why. That's weird. Let's try again. And it doesn't work anymore. Okay, I'm going to try to somehow, just a second. Logitech FaceTime. Let's try to do this. I need to say like this. All right. So the point is here, it's cheaper to call support than to implement some kung fu like I'm going to show you in the next 15 minutes, right? And you implement a Saga like I'm going to show you only if you have failures like this too frequent or too expensive. If your clients start calling customer support, customer protection, if you have to pay like reimbursements, money, like penalties, then you start thinking about the Saga. So what the heck is a Saga in the end? Let's see. I will go to the one which is really, there are many flavors, some of which are completely sick, like this one. In a synchronous LPC Rest Style, you call 3 systems, and you hope all of them are going to give you acknowledge. This is sick because the orchestrator takes a lot of heat, a lot of risk. If any one of these times out, if any one of these fails, this guy is going to fail. It's extremely dangerous, this approach. No one does it, really. What people do is asynchronous Saga, using messages on queues. And there are 2 main flavors of a Saga. The first main one is actually too much. The first flavor of a Saga is orchestrated, in which we have a boss coordinating the whole flow. The other solution is choreographed Saga, each with its own pleasures. Let's analyze both of them first. Orchestrated means there is a workflow manager. And maybe it helps if you relate to some libraries you've heard of, Camunda, Apache Camel. There is a workflow manager out there overseeing the whole flow. If it sees an error from this guy saying, oops, I don't know, the shipping provider doesn't agree to ship this fridge at that mountain peak, 2,500 meters altitude. They can't because they don't have mules. In Romania, the highest peak is Mountain Omu, 2,005. They only bring mules. You can ride ATV. Yeah, imagine someone carrying a fridge on an ATV. Maybe some helicopter. They don't have helicopters. All right. And if the shipping says no, the orchestrator can go back to the previous parties, cancel the stock reservation, undo the payment. If undo the payment fails, it's going to repeat until it succeeds, because the compensating action should be idempotent. So this is what happens. On error, the orchestrator will send compensating commands to undo what happened before. Okay? Why would I need the fridge? Peter, come on. Good. Choreographed. Now, in this whole microservice world, it is somehow considered to be not smart, not safe, not, I don't know how to put it. Orchestration-based workflows are not as fancy as they were in the SOA times. Nowadays, if you heard the principle from Martin Furrer, I personally heard it first. Martin Furrer said a lot of good stuff about microservices. You should be reading his blog daily. Smart endpoints, dumb pipes. Smart endpoints, dumb pipes. Here, article in the chat, in Zoom. The idea is here that you don't want some smart middleware to be orchestrating your flow. You don't want to have all these microservice teams depending on the SOA team, on the SCB team, on the, how is that called? Mule. Oh, by the way, Mule, ESB, the Camunda workflow manager guys. You want more independence more autonomy in microservices. For that reason, we generally prefer for a more choreographed solution. Now, in a more choreographed solution, recovering an error is much more painful. What options do you have? In such a case, there is no workflow manager overseeing the whole thing. But instead, each party in the chain knows who to message further. Now, this again has two flavors. Service A could send to service B a command, which means a point-to-point communication, or it could fire an event at which B reacts. Again, flavors. But when B does its work, it might send further another command or event for which C does stuff. So the execution is now in C. Imagine what happens now if C fails. They don't have helicopters. I told you. What happens then? Shipping, there are several solutions here. Probably the worst solution is for the shipping to message individually to all the parties upstream. That means coupling, a lot of coupling, to send messages to all the three parties before. It's a lot of knowledge for this guy to keep, right? That's why what can do, you can publish here an event that shipping rejected event, and those guys over here would listen to that event. But that is also coupling, because suddenly A and B have to know about C. Why? Why do I here have to listen to C? You see, this is a bidirectional, how to put this? Not fun. Why should A know of C? Right? A should know of B, okay, but not of C. This is ugly. This introduces coupling, confusion, and if these are different teams, God help us all. Right? So what next? What you can do instead is another fancy solution, but again, no one. Yeah, a trace ID would help here, Adi, you're right. The event that you've thrown out saying shipping failed would carry the trace ID of the flow. But then I still have to listen to the shipping failed, and I'm payment. I should only know about stock, not shipping, you see? There should be a correlation ID, the order ID, the trace ID, some business key to relate to, of course. If orchestrator is a business concept aggregate, then it still comes way Bukaj. If orchestrator is a business concept. Can you explain in more words there, please? B listens to C, yeah, that could be a solution. C fires an event, E listens to that event, undoes what it did, and fires another event called how? Stock failed? But it's not really correct. You are really failing because it's not natural, right? Not natural. There's an event. Nah, I like unwinding the flow. Nah. What you can do, however, it's called the routing slip. It's a madness of a pattern, which goes like this. Every time one of the parties involved sends a message further, let me do it again in one single line. Yes. Whenever a party sends a message further, it will add to like a stamp the endpoint to call or the queue to send the message to in case of problems, to undo what it just did. It gets here, This guy adds its own undo, sends the message. When there is a failure in the third message, the third party takes these and blindly calls these endpoints or fires on these events or those queues. Like a callback. But it's insane. In 18 years of practice, 10 years of consultancy, I never saw that in practice. It's called the routing sleep pattern. It puts a lot of pressure on the microservices over there. They need all to be in the same boat, in the same mindset, in the same idea. They all have to know about this convention and propagate further their stuff. Ugly, right? Ugly. So what some people use instead, even in the choreographed solution, they used the so-called Saga execution coordinator straight from Biodunk, which is a separate system to which all the parties involved in the choreographed flow are announcing where they are and publishing how to compensate in case something wrong. So instead of having everyone responsible of canceling upstream, you put that responsibility to another guy, which sits there just in case of problems. You push, and that guy keeps a log of where you are. It's, if you ask me, that still seems as a sort of orchestration. There is someone here to oversee the things, but you only use it in times of trouble, when I find myself. So the point is here that you push the state, hey, I've started transaction 1. I finished transaction 1, yeehaw, right? Tick, tick. I've started transaction 2, oops. And when oops happens, then Saga, knowing how to compensate transaction 1, would go and say, cancel what you did. All right? This is kind of the idea around here. It's kind of an orchestrator, but it's choreographed because this guy does not decide what happens next. It just records the undos to do in case of problems. Exactly. The coordinator here only manages the failures. It will not drive the flow. It does not have any decision to take that path or that path. Doesn't have that. It will just be called in case of trouble. That's it. Right. Nice. Okay. Fun. That was a fun journey. Now a bit of basics again. Just one simple thing. If you design sagas, you will have to understand state machines. If you design sagas or you program Saga using a tool, you need to have in your knowledge what the state machine is. What if the message to coordinator fails? Of course, with 120 people in the room, of course someone thought, hey, what if I can't communicate this? After a while, this guy is gonna cancel automatically upstream. So you have a time frame. Hey, the T2 should finish in that amount of time. Or you could use the robust outbox pattern used with a durable queue to send to this guy. Yeah! Laser! Yeah! Right? Just to have tricky. Right. State machines. We all went to supermarket. To get this freaking cart from the supermarket, we need to push a coin in here. Right? Unfortunately. So we have the locked state and unlocked state for the cart. Initially it's locked. To get it out of the chain, you need to push a coin inside, of course, which unlocks it. Now, of course, you can insert more coins, but you probably aren't very smart if you try to insert another coin. You can't. In that state, this transition, this action is not possible. We can't insert more coins, right? But once it is unlocked, you can drive it through the supermarket. Once you're done shopping, you will push it back in the stack and you'll get your coin back. Now, if it's in the stack and you keep pushing it, again, you are a bit dubious. Why do you keep pushing it? It's there. Stop, right? So there are some transitions which are invalid in a state machine. However, every such external signal, for the cart, this is an external signal. It gets a coin from me. it gets pushed in stack. It gets payment accepted event. It gets payment rejected event. For every such event coming to the state machine, the state machine reacts with an action. Grabs your coin, right? Releases your coin. This is the action of the state machine. So you have to model such state machines if you want to understand the saga. So it moves into a certain state. What happens if an event of that type comes? What happens if I never push it in stack? Probably you need a timer here to say if I'm not pushed in stack in 1 day, call police. Someone stole me, right? So also time. So they saved us during COVID. We would have starved if it weren't for these guys. So for the last 5 minutes or so, we're going to try to design a little, to see how it feels, to understand the ideas. A food delivery app to feed the hungry people with good food from restaurants delivered by couriers. And of course, for a fair price. All of them have app installed. Okay, let's fast forward this decision here. The first thing we want to do, of course, is take the money. Oh, actually, the first event here is that the hungry customer orders food from a restaurant. Perfect. The first thing we want to do before anything else is to get the money. If the guy doesn't have any money, even if it's hungry, we don't care. All right, unfortunately. You get the money from the payment gateway. Perfect. Then the second thing we do, we tell a restaurant to cook food. Do you smell pizza? Pizza. It's already hot in the... Then we locate the courier. Then the courier picks food from restaurant, delivers food to customer. And then at the end of the month, probably, we charge a fee to the restaurant for our service. To the restaurant. They have to pay us somehow. Cool. What can go wrong? In the chat, please, if you can, put some ideas. What can go wrong? I'm curious. What failure modes can you find to this? Everything. Come on. Wait. No courier. No courier available. Which means that if I find a courier, no one wants to drive to Mount Omu to deliver your order to 2,500 meters altitude. Okay, what do you do then? Well, let's see that first. And I was sure that. Oh my God, the YouTuber, they should be in Zoom. They are insane here. Good. The courier is not found. What should I need to do next? Well, but it was already smelling like pizza. Do you see the problem? What? Let me try that. Hello, restaurant. Cancel the pizza. What do you mean? It's cooking. Cancel. Put it off. Take the sausage off. Take the parmigiani off. Cancel the pizza. You can't do that. So here you have a problem. If the restaurant starts cooking the food, we can't undo it. This is a not undoable flow. No fridge? What are you doing? So this is one case in which you want to do a reservation. We will tell we may tell the restaurant, hey, reserve us the ingredients to make us a capricciosa pizza. We find the courier accepts, and then we go back to the restaurant to confirm. In which case, the restaurant pulls the pizza in the oven, and we're good. It starts cooking. Okay. The restaurant does not pay the fee. For that, we have the legal department. No problem. Customer cancels. I mean, it's not a customer visible, Georgita. That the restaurant doesn't want to pay the fee. That's not a customer facing. It's a restaurant facing. So we can call the lawyers to attack them. Right? We have a contractual form. Right. Put in the queue to wait for available courier. Yes, we will find the courier in a time frame. Like we can spend 1 minute to wait for someone to confirm. Okay. So there is a reservation that should happen over here. Find the courier. But still, if I can't find the courier, I need to cancel my reservation. Go back to the payment and say, hey, you know what? Cancel payment. idempotent repeat until it really succeeds in. To be honest, the payment gateway usually does not really get, most payment gateways don't get your money on the spot, most sellers, but they block an amount. They do the same thing. They reserve an amount on your card, waiting for a confirmation further on. Okay. What else? Customer cancels, but order still arrives. It's in the terms. If you placed an order, we charge your money. That's it. If you leave home, it happened to me. I left home. The courier was on the door. Ding dong. My wife ordered pizza. I didn't know. I was halfway to Brazil, and that guy, hey, where are you? Eat the pizza. That's what I said, the guy. Eat the pizza. Thank you. It's yours. It's yours. Restaurant has too much orders. In that case, it will not accept my order. Although that will be a business loss for them. Wrong food. They only sell chips. Restaurant doesn't cook food. Yeah, if it does not cook the food it promised to cook, legal department. Then when you call, then it's when we involve customer support. They say, we are sorry, the restaurant. Can we get you a pizza from another restaurant? I actually heard. I have a friend that was called by one of these guys to be proposed another food from someone else because the restaurant, I think they closed the restaurant just then and they didn't get to finish the order somehow, something like that. The order got lost in the transit, something on the restaurant side. What else? Delivers to wrong customer. Julia, you are too good. So someone which doesn't have money will eat your food. All right. It could happen. In that case, again, we will apologize to the customer, but it's tricky to find out that happened. The customer might. Another thing here, that's another problem. Okay, the customer received the food. How would you know that? Big problem. The courier must say, I delivered, and within a time frame, if the customer complains he did not get the food, it's tricky. That one is tricky. But sometimes to save the business, to save your image, you might tell the customer, look, we're gonna ship you another food. They don't do that, but you could. Government raids the venue due to us. Courier gets bike stolen. The courier gets hit by a car, God forbid, right? And he never gets to deliver the food. Right? For all of that, you can think of compensations, and these are basically transitions. Courier hit by car event. God forbid. I really hope. Oh my God. Okay. Yes, indeed. A good customer support can fix most of these problems. Most of these problems. Right? I actually heard some stories about customers of pizza factories, pizza restaurants that were placing an order for some pizza, and then they what did they do? My God, they never not confirmed. They tricked somehow the system, so they got some pizza that no one picked up, something like that, and they eat the pizza. This can be abused, of course, but the idea is that customer support. Look, if I log error with this token in my log, there is an alarm raising somewhere in a support team saying, hey, we need to jump in, and then attack. That should be the first, yeah, we need to finish this because people are getting hungry. So that should be the first go-to, some support. And if it gets too expensive or too embarrassing to cover for your losses, or you just are too frequent, basically, when the customer support riots against you, then you need to do something automatic. You play a Saga. With one of these, don't reinvent wheels. Study these, if not use them, and see how they do stuff. And right. Now, it's been an hour, and I should keep in the time. Still, people are talking about pizza everywhere. Wait, Spring State Machine. Whew. If I were to choose between these and Spring State Machine, I would choose one of these, for sure. I mean, like, Spring State Machine does not cover for distributed systems. It's a good implementation for a state machine, but then you have to play all that messaging in, messaging out yourself. You have to think very hard. Others have taken this to the next level, such as Mark Richardson, who is the author of Microservice Patterns, who is the author of this framework. Right? There are big players in here. It doesn't mean don't need to reinvent wheels. Now, folks, I will ask you one thing. Technically speaking, the discussion is over from my side, but there were some messages on YouTube that I glossed. I will ask you, please, all of you, be kind to me and re-ask the message you had if it wasn't answered by one of the participants, so that I know what to read. Copy paste the message if that's not. Axon server is a pain if you don't use Axon server. Yes. Stay away from Axon. As a matter of fact, that's very. 2 teams I know, 2 out of 2 that I know using Saxon regret it. Outbox. So let's see. I will now start answering the question and pasting the questions in front of you so you see what I'm answering here. What if we have parallel transactions? The first one takes longer. So the outbox. Oh, nice. 2 threads. Red thread, green thread. Maybe if you want to hold on for a second to answer this and then paste and enter to send your question. The first message, the first transaction starts here. Takes longer than the, let's say, time flows down. The first transaction starts here and is longer. The second transaction starts here and finishes immediately. However, since the commit of the first one technically happens after, there is a problem. I think that's what you mean here. So the red thing here generates the event with sequence. Let's put in the red sequence number 1, and the second one, this one, commits before the first with sequence number 2. Exactly, that's what you meant. The global order of events is lost. The recipient will receive out of order events, and we're talking about transactional outbox pattern. The recipient, the poor recipient, is going to receive the green message first, and then the red message, even though the red message was caused by a flow starting before the red flow. That means that the recipient needs to be able to reorder the message. It's tricky. That in the messaging pattern is called a resequencer. Folks, we are reinventing wheels here. I hope you know. These are the classical messaging. These are the classical enterprise integration patterns you should read about. All these problems have solutions. In a very old site here, like 10 years ago, we were talking about this. What you need here is a resequencer. Is some endpoint that is able to get the messages out of order, reorder them, and issue them in the order they should be. Someone that has semantics about what the order should be. Tricky. Sometimes it's almost impossible to do that. Almost impossible to do that. All right. But you need someone to have the semantics of what happens in what order should happen. Right? That's the best I can do in this time. Let's see what else. Outbox plus CDC exactly once. If your message has an ID, I think you can. That's a question that I should ask ChatGPT. Not sure. What? Not sure. I believe it can do that. I believe it could have the meaning. Look. At least once. There are situations in which the connection between the database and the BZM running in it and the Kafka broker could fail, and the message could be issued twice. So this doesn't mean your endpoint. It still means that your endpoint should be, your message consumer should be idempotent, right? So no, it's not the design. But again, if you just look at the message ID, you could actually, if you want to get this responsibility out of the listener, you could introduce in between here another super tiny endpoint, not necessarily a full microservice, just maybe a simple message listener that using a list or a set of the last seen messages today, gets the queue in, removes the duplicates, and then pushes exactly once on the closer to you, basically. It's 3 lines of code in Spring. Spring state machine is too light for the problem that it solves. It's just supposed to take you to make a state machine implementation just like the BPM solution does. It's just like a BPM on-prem in your code. Too light. No, it's Recording of the session, yes, of course. It's already linked in the meeting on the community. Yes, thank you. All consumers should do this or only one server? We are talking to what? The detail, Adam. I'm gonna skip the question until that. Would the cancellation topic help? Ooh-la. All involved entities would publish and listen to the topic, and each message contains at least a trace ID. Oh, so they could know what they did for that trace ID and know by themselves what to undo. That way, there is no need for specifically event listeners. Right, like general purpose, but then that means that every listener that can undo needs to keep track for a trace ID what action they did. So I'm seeing right now an internal cancellation table. So it's like in which I know for the trace ID what operations I did. I take these operations and I have the name of the operation that I did, and I undo the operation. Could work. But that's actually the purpose of the Saga transaction, Saga execution thingy there in the slide. I will put the slide again. This. It will actually tell you what action you did, and you put them in a central place. Now, you don't have to push the responsibility in each of these, but that's another solution to the problem for sure. Let's see what else. In banking, this is called coalescing. Wow. Coalescing in English, because I'm not a native, means come together to form one mass or whole. Combine the elements. You mean like having two events and then merging them together as a single event? That's called an aggregator in the integration patterns. But perhaps you were talking about message number one, message number two, that needs to come in a certain order. That's another solution. You can wait for both and issue instead of them a single message with both information inside. It's generally not a good solution to just Axon Saga. Vendor lock-in for sure. Axon will lock you in forever. Keep the cancellation table for a few hours. If your flow is maximum to take several hours. Because for bank systems, some loan approvals, you can take more. I don't know. It depends on your domain, of course. How would you consolidate events from multiple Kafka topics? But they needed to be in order. That's one solution. You would create a new topic and publish messages, not twice. Aggregator. Two Kafka types of events. Event one, I just draw that. Event two. This thingy, aggregator, which I issue further E1 to a single event. Maybe. If I want to protect the end listener to receive a single event, not two. And let's say we can't have event order number. But how would you correlate them? One solution I've seen in a client of mine, they were waiting for a certain time frame. Event one came in, and they were waiting for 1 minute for other events related to the same ID to come. Whatever came in that minute, they will bundle together in a single large message and ship away. That could work. Again, depending on the domain, you might lose things and so on. Let's say that we can't have because we don't have event order number. Right, YouTube now. If there are any questions repeated, let's see. When attaching a timestamp to the message to keep track of the order, what is the clocks of the system? Oh, man. Oh, no. True. Especially if you have the different data sources far away from each other, it's really a problem. Use the Redis to keep track of the event ID and talk to the Redis to get the next event. That's actually one of the biggest problems in two-phase commit. To have the times in sync. That's actually a security vulnerability. Let's just talk about GVT expiration token, but you're not talking about a time skew of 1 hour. You're talking about a time skew of 2 seconds, not more. And a message sent in Australia would appear to be sent earlier than a message sent from over there. Tough problem. So the message is emitted about the same ID, the same concept, the same thing, if you emit them from far away, take this problem into account. If you are basing your reordering for a time skew of just several milliseconds, if the times are, so then you come back to that idea that you delay your messages in transit to take all of the messages, right? Get all the messages in, but you still can't know which one will send first. A tough problem, really tough problem. I don't know how to fix that, except only maybe doing a call to some central time server to get the timestamp from a single place. I could imagine that. Sender 1, sender 2, having a time server that they call with a REST call to get the timestamp, and they keep asking for a timestamp until they get one, and only then they send the message. But if you are in the same data center, that should not happen. What is the conclusion after the presentation? The overall conclusion. I just tried to show you some ways to preserve consistency across distributed systems. So we talked about transaction outbox pattern. We talked about idempotent endpoints. We talked about idempotency in general across. Let me recap by showing the slides. Right? And the general conclusion is to try to stay away from Saga as much as you can, because it's extremely heavy in practice. Extremely heavy in practice. Let's have to put all of them together. Can I fit them on the screen, all of them? Let's see. Here, this is what we covered. We talked about CAP theorem, that you can't really get both at once. We talked about two-phase commit, told you that not very fancy for microservices. I talked to you about that designing in a different way the services could avoid problems of maintaining consistency, right? Avoid synchronization. We talked about retries that only are really allowed if you have idempotent operations, both endpoint and HTTP or message listeners. We discussed how to send a message in a reliable way in the same transaction as the database updates. Also how to consume a message and how to acknowledge it, some things that many people don't really take into account. Transactional outbox table, and the Saga pattern with some machine that keeps track of where you are and undoes the stuff you did, or that you distribute the responsibility in all the parties involved, which increases the complexity quite a lot. And the state machine concept that you need to be familiar with if you play a Saga or if you design a Saga in whatever framework. Great, complex topics, these ones. This is what scares most adults playing with microservices, eventual consistency. This is what frightens us more. Eventual consistency versus full consistency. Consistency, there was another issue with consistency about the CAP theorem. Just let me search for that. CAP. Just a second, please. It was in the theory part here somewhere. Sometimes it does not work. Sometimes you don't need extremely precise consistency because the real world sucks. It doesn't help if you strive a perfectly consistent app if 10 kilograms of tomatoes just got spoiled in your stock, or if an item is out of stock. If it's not out of stock and you get an order on that, you can ship it directly from the external supplier with 3 days delay and apologies over the phone. The courier did not find the exact product, but gets you something similar. Good enough. The player sees level up after 2 seconds of delay, right? There are many things in the real world that you can't really maintain perfect consistency. So at some point, it is not worth traveling that much. Go with the inconsistency and think of a way to recover. And at some point, inconsistency can be exposed to the business, and the business could tell you, through consistency, we want availability more. That could happen. It happens many times. Well, I think I finished all the questions. Oh my God, right. So not to intrude more in your personal life, I think we're gonna end this now. It's still recorded on YouTube, I said, and that's it. And I will think about a way to have a panel at some point about architecture. It keeps bugging me because people started challenging many architectures that I was thinking as golden standard recently, and I want to have a debate with someone. Slides. Yes, I'll publish the slides on my on the community over there. I'll put the link to the community once more commercial, and we'll end in several seconds. Here, join this. It's super fun. Right here. I'm gonna put them here. Good. And with that, thank you all for your time, and see you the next one. All right. Have a great, wonderful evening. Good. Bye, folks. Bye. And we are ending this now.